We recognize that sometimes true or false statements can be recognized by zeros and ones. Sometimes can be zero, sometimes can be one. How about if I tell you that they can be both, or partial of zero, partial of one at the same time? It's called quantum. This is the Hacker's Corner. Adversarial Thinking Edition. Hi everybody, welcome back. Welcome to the Hacker's Corner. My name is Servín. I'm a professor here at El Paso Community College. I teach here the cybersecurity classes, computer sciences, and recently AI with a combination of other items. This is the Hacker's Corner. I want to welcome everybody. I want to thank everybody who has been very pending, and actually for all the comments that you've been sending to us and put it in the YouTube channel. I want to thank also for those who have been sending us emails for suggestions, comments, and of course discussions. So the whole purpose of this show is to provide awareness, cyber awareness, different type of awareness about the emerging computing areas. And we're doing an adversarial thinking series for the broader good. As you know, we're running this program and in a collaboration with a couple of affiliations, as you can see here in the screen. So please join us to the hackathon that we're gonna have soon. It's called Hack the Border version 2.0, as you can see right here. We're running a series of different events, including professional development, and of course, a couple of big events prepared for the border community and for you who have been seeing this show. Of course, today we have a special guest. We have Mark here with us. He is the CTO and the Quantum Village co-founder, and we're very happy to see you, Mark. Can you hear us?
I can hear you. It is a pleasure to be here.
Mark, tell us a little bit about you. We have this remote connection with Mark because he is in a different country. Right now, we're in El Paso, Texas. Where are you right now? Can you disclose that information?
I'm in an undisclosed location in the middle of London in the UK. So my name is Mark, better known as Mark C, sometimes even known as the Large Cardinal. I've been into cybersecurity, hacking, if you will, for a long time. Most of my life, as far as I can remember, I've been playing around and tinkering with computers. And recently, that exploration has taken me into the world of quantum mechanics and the world of quantum computing, and asking the questions that a hacker would ask about quantum computers now, like where are they going to go? What's going to happen? Are they a threat? How much of a threat are they? And also, how are they vulnerable? How are they vulnerable themselves to attack and to manipulation from outside? So this is the kind of thing that I'm looking at almost full time now. So this is very exciting to be here discussing it with you.
Absolutely, I agree with you. Mark is a quantum hacker. I met him on DEF CON. Actually, Mark, I met you 2 years ago. That was the very first time I went to attend to the Quantum Village, and I was in the, I think it was capture. It was not capture the flag. It was capture the package, and then there was this. It was not small amount, but there was some people who were congregating there, talking about very exciting topics and talking about interesting discussion. It was an interesting discussion about quantum. It's like, what is this? And then I checked the whole conference item. Is like Quantum Village. Is like, this is true. And then I saw you there leading the whole process. It's like, what is what is all this? And I thought it was like, this is great. So this year, 2023, I said, I love DEF CON, but I'm going to go and sit in one village for the next 3 days. And that was a Quantum Village, because for me, it was an exciting vibe, exciting movement, exciting progression of how cybersecurity, how meets the computing emerging technology, in this terms, quantum mechanics. And so this is what I've been looking for many, many years. And then you were talking about different aspects. You were coordinating the entire village for 3 days, and for me it was fabulous. Tell us a little bit about the Quantum Village.
So we are the official quantum village at the DEF CON conference, as you mentioned. And we've kind of tried to set it up as a very open space in which you can come and explore, you can engage with, and you can discover new things about what we call quantum technologies or quantum information science and technology. And we wanted to create a way of getting different people who are passionate and technical, but not necessarily with PhDs in quantum physics or mathematics, to come and engage with this technology. It's not just for people who have PhDs. I mean, if you have one, that's great, absolutely brilliant. But if you don't have one, it's very common to think, oh, it's not for me, it's too hard, it's too difficult. And I'm here to tell you it really isn't. And we want you to get involved and come to Quantum Village and experience this amazing potential technology. So that's what we set it up for. The first year, we weren't sure how it was going to go. Are we going to get booed out of the conference, or are we going to get some kind of some fan club? And we ended up having a really good time, and we were standing room only. And then this year, we repeated it. We were really full. We had loads of really interested hackers who wanted to come and just learn about what quantum computing is, what quantum networking might be, and where quantum sensing might come about, which are the three big areas of the new revolution in quantum technologies.
Mm-hmm, mm-hmm. And you mentioned, I think you mentioned something very important. When I talk to people or people who say quantum, I'm sorry, I don't have a PhD. I'm not very good in that math, and no, thank you. You mentioned something very nicely. It is okay if you know those concepts, but if you don't, there's room for you to in order to explore more areas. And we have this conception about quantum is super difficult to measure, super difficult to study, but in reality, it is. In reality, it is. But in reality, it is. There are ways to actually disseminate this information. Right now, there's a couple of efforts, and I think what the Quantum Village is doing, you're actually breaking those barriers that for generations they have been created about quantum. And I think you're creating this, you open this channel to bring the new generations to study this emerging computing area. I'm not so sure if I should mention emerging computing area, because quantum is being there for a while. It's been just now that we have a lot of progress nowadays in order to see the actual content going on. Tell us a little bit about what is quantum and what is important.
So Quantum Village aims to cover many different areas, from security to sonification of quantum technologies. But fundamentally, we're dealing with a way of computing that focuses on, or a way of doing technology that focuses on the atomic level in a different way than, say, nuclear physics. So what we're trying to do here is you're trying to utilize one of two or both concepts from quantum mechanics. And those two concepts are superposition and entanglement. Now, superposition is quite easy. If you've ever heard a sine wave, that's a nice wave. And when you put more sine waves with it, you get different sounds. So if you take some sine waves, you get a piano sound. And other sine waves, you get a guitar sound. And those are just superpositions of different waves, giving you that overall sound. And so nature, at its fundamental level, has a superposition, not of sounds, but of energy levels, from which we could build information about and program now information about different processes. And what we've found is that we can harness these particular properties at a quantum level so that we can actually use them to do useful computational work, which is amazing. So when you think about how we do that, one example, which sounds totally sci-fi, is they're called ion trap computers. They're a really good illustration. So here what we do is we create a vacuum that's emptier than outer space. We then make it cold, really cold, colder than outer space. And then we suspend these individual atoms in little radio frequency cups. They're invisible. You can't see them. And then we shoot them with lasers. Like, this is all sci-fi. And with that, we can do computing. We can actually solve problems that right now we don't even try to, because they're really, really hard. Mathematically, we know that they're really, really hard problems. But by coordinating all this physics and all this science, and by coordinating what we call quantum information theory, we can actually carry out useful computations that would allow us to surpass what current computers can do.
When you mention cold, because you're talking about very cold temperatures, right? It's not like you open the freezer, it's like, oh, this is cold, or just wait. In El Paso, we don't know cold, by the way. We live in the desert. But I once went to Alaska. I lived in Alaska for a while, and that was pretty cold, like negative 36 Fahrenheit. Are you talking about that cold?
Oh, that's really warm for an atom. So we're talking about millikelvin. So
Wow.
Kelvin is a completely different scale of temperature. You don't usually measure things in Kelvin because room temperature is 240 odd Kelvin,
Wow.
250 Kelvin. 0 degrees Kelvin is what's called the absolute zero. And theoretically, we know we can never actually get there, but we can get really close. Outer space is about 3 Kelvin. So it's really, 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 really cold. But we're going beyond that from
Wow.
3 Kelvin down to 0.01 Kelvin. Like we're talking, decikelvin, centikelvin, millikelvin. So we're making things really, really cold. And the reason we do that is because quantum states are really fragile.
Mm-hmm.
So when we create a quantum state, if we didn't have it really cold, then the state would just mix with the states around it. And all that work would be for nothing.
Exactly.
So what we do is we cool it to maintain stability of those states.
Wow, that was a beautiful explanation, by the way, because in many different conversations that we have had with other quantum physicists and quantum mechanics, they say like, oh, don't worry, they're cold enough, but you're shooting lasers to do those lights. So now you're talking about lights that get transparent through the entire atom, or not atom, I'm sorry, you mentioned photons, right? When you talk about computations, I don't want to introduce another complexity, but the complexity of time now plays an enormous role, because computational time, talking about the real time that we're living here, usually in computers we're talking about nanoseconds. Now we're going to talk about quantum time, which is a completely different conversation, right?
Yes. So what we're talking about with the possibility of quantum computers is the fact that if you have a load of qubits, so bits are just switches, right? They're on or they're off. And so if you want to have lots of different representations of different numbers, you have to have lots and lots and lots of switches.
Mm-hmm.
And then you arrange the switches and you do things, actions between them. We call them logic gates. Then we can perform what we call a computation. And this is an idea that's nearly 100 years old. It comes from Alan Turing and from even older than that, George Boole from the 1840s. So we're comfortable with this idea that we can represent everything as zeros and ones, and we can do things between them. And then we can get a result that is in some way meaningful. What we do with quantum computers is we allow qubits. So a qubit is a quantum bit, and that has a special property. It can be 1, it could be 0, it can also be halfway between. It could be in what's called a superposition of 1 and 0. And so we're able to put these various answers or inputs alongside each other and then use quantum gates, like logic gates, but quantum.
Mm-hmm.
We could use quantum gates to actually set up what we call a quantum circuit, which is just a quantum algorithm. So all these things, it sounds like you've just taken all the things from regular computer science and put the word quantum in front of it. And that's pretty true. You have just kind of taken all these ideas and then put quantum in front. But in doing so, you've also done the math so that everything lines up in a way that doesn't break physics. Because if you break physics, it's not going to work. So what we do is we can perform algorithms in a very similar way that we perform algorithms on what we call classical computers. But because we have these quantum effects, we can do more with them. So I can put more possibilities into a superposition and use quantum gates to find the answer I want within that space. And I can do that in fewer cycles. And that's the promise of quantum computing. It's called the quantum advance.
Wow, this is very very interesting. The fact that we're living in a moment where we can actually formulate this theory in nowadays, I think seems to be. You mentioned sci-fi because back in the day we thought, well, later on in the future. This is the future. Um, we live in El Paso, Texas, and a couple hours away from here is Sandia National Labs. And they have a quantum computer. And they have a big team, great friends there as well, who have been talking about quantum physics, quantum mechanics, and how can we use this. The quantum computers, have you experienced anything with quantum computers? I'm going to talk about a little bit about the synthesizers that you create later on, but the quantum computer itself, have you been exposed to one of these computers, and tell us how it looks like, or what is the whole purpose of this quantum computer?
So they look really amazing and impressive when they've got all their clothes on. So underneath, when you see one normally, it's just a big stand with a really big tube in the middle, and then lots of circuitry around it. And this is all the control circuitry that manipulates the qubits.
Mm-hmm.
The actual quantum computers themselves have different shapes. There's different kinds of qubits that can be used. The most common one you'll see if you Google quantum computer is it looks like a chandelier, this beautiful big golden chandelier. And what that is that's not the actual quantum computer. That's the cooling refrigerator.
Wow.
It's called a dilution fridge. And it's got all these different layers. And the physics that it does lets you go from 4 Kelvin to zero point 0.4 Kelvin to 0.04 Kelvin. And then right at the bottom, if you look really hard at those photographs, is a little tiny square. And that little tiny square is the quantum computer. That's the magical chip that's doing everything. And it's made from silicon, just like regular computer chips are. It's just that it's made from a very different arrangement and build and structuring of silicon, because it has to survive those temperatures, and it has to be able to handle all these different control signals coming in from the controllers outside. So you see the quantum computer, then there's all these other banks of machines around it that are controlling the timing and the microwave controllers and the signal generators and all that sort of stuff. So quantum computers are a lot more than just this beautiful chandelier. If you want to have access to one, you can go online for free and do it now. If you go to IBM, say, you can connect to IBM Cloud and you can just access a quantum computer. And so now you're seeing that there's even more there. So you put your circuits, your algorithm in, and you press go, and then it goes through all of this cloud infrastructure. So it goes from cloud to classical computers to the quantum computer, and then all the way back again to give you your result. So a lot of the quantum computer is actually very classical, and we understand it very well. And one of the things we've been asking is, well, if so much of it's classical, can we hack it? And so this is, of course, the natural thing that we get to being hackers, is we want to get to know so well this technology and how it really works, what's really going on.
Mm-hmm.
But when you see them, they are beautiful machines. They really are. They are a pinnacle of our science and our engineering.
You mentioned that there are available computers. Are these simulators, or they're actually quantum? You have access to the quantum computer?
You have access to the real quantum computer
Wow.
itself, which is amazing to think.
I think so.
You can actually submit a job and for free, and it will go into a queue. If it's busy, that queue can take hours, maybe even a day or two. But if it's not too busy, then you can just send information to the quantum computer, go make yourself a nice coffee, you come back, and you'll have your results. Now, it should be mentioned that these quantum computers are noisy. So we're actually in what's called the NISQ era, NISQ, and that's the noisy intermediate scale quantum computer era. So noise creeps in, and the longer your algorithm and the more complicated it is, then the more noise you can introduce. And because of that, the answers aren't always so crystal clear. What we're waiting for is the quantum error corrected age, where we have one qubit that's actually a group of lots of physical qubits, and they kind of are meshed together in a way that lets them correct for noise, which means that the algorithms that you run will have much better fidelity. It's the same idea that we have in, say, Wi-Fi or in regular computers, like in RAM, when you have all these parity checks and things. It's the same kind of idea, except that it works in quantum systems, not classical systems. So we're building up, but if you go on there, you can absolutely use a real quantum computer.
Well, that's amazing. I would never think that we could have access to a quantum computer through our own machines. And of course, probably that requires a lot of programming skills, or what do we need to know?
It really doesn't. In fact, if you can drag and drop, there are interfaces where you can just copy the image from a paper, make it look the same, and you'll be doing the same algorithm because we understand the mathematics of this really well. So you can kind of just code it that way. You can also, if you know a little bit of Python, you can code it directly in a Python interpreter. You have to use a library such as Qiskit or Bracket from AWS or Penny Lane from Xanadu. And they all do things a little bit differently. There's one from Google called Circ as well. Like they have different features and different interpretations of what's going on. But you can code or you can just drag and drop. And when you press go, it'll send your circuit to the quantum computer and give you the results.
That's amazing. Talking about quantum, I mean, at least 3 days it took us to go through the DEF CON Quantum Village. It's going to take a while to talk and unpack a couple of things here, but they've been talking about the importance of quantum in cybersecurity. And also they told us once the quantum computing is out there, forget about your privacy, forget about everything, is going to be gone. Why people say these things?
So in 1994, there was a paper from a guy called Peter Shaw, who's a professor. And he published a paper that showed that you could do a really amazing thing with quantum computers. You could solve number factoring. Now, number factoring it sounds really boring. And to some people, it probably will always be boring. But number factoring is a hard problem in this way. If I give you 12, right? And I say, which numbers did I multiply? Well, it could be 12 and 1, it could be 6 and 2, or 3 and 4, right? There's a few options there. But if I give you 2 and 6, you can easily check, oh yeah, the answer is 12. So going one way is really easy, but going the other way is quite hard. And the bigger the number, the harder it gets. And our modern cryptography, so the mathematics that we use to secure and encrypt data in transport when it's sitting on our hard drives, that mathematics relies on number factoring being hard enough. Now, Peter Shaw's paper came along and said, well, quantum computers are going to basically make it straightforward to factor numbers, which means that it's going to be straightforward to reverse out our keys from our encryption algorithms. And there was another algorithm that came along around the same time by Love Grover called Grover's search. And this allowed us to take any known plain text ciphertext pair, put them together, and get the key out. And it does that in the square root number of tries it would take before. So what does that mean? It means it goes from being, say, 128 to just 64 tries. From 1024 to just a small number of tries. And so because of that square root collapse, what happens is that we lose track of the security. So we can no longer rely on number factoring. And that's why there's a lot of cybersecurity chatter around quantum computing, because there's this potential. I mean, there's a lot of caveats as well. Like we're assuming we can make big enough and cold enough and accurate enough quantum computers. But those are all engineering problems. Like the mathematics says that if we can make a quantum computer of a certain size, then we can perform this algorithm called Shaw's algorithm or Grover's search algorithm. And with those, we can actually attack modern cryptography. And the nightmare scenario is that someone gathers all of our data, they harvest it now, and then they decrypt it later and open it up. And that might not matter for some things, like how much I paid for my Starbucks this morning. But for certain things to do with, say, legal documents or to do with business documents or privacy documents or medical data, that could be quite damaging if that was decrypted and exposed. So what we're looking at is ways of protecting that moving forward, but that's what we call the quantum threat.
Wow, amazing. So adversarially thinking, if we would like to put it in the context, is like once we understand the possibilities of refactoring and of course the composition, we can actually hack the entire algorithms of encryption. RSA, I believe, is right now the one that we have as a standard, right? RSA, and that will be completely breakable.
We can make the keys even bigger. That's one way to get out of it. You've got a big quantum computer, so you just make the keys even larger, and then they should still be safe, right? But the problem becomes that the keys get so big, they get bigger than the data itself really quickly. And then you're only after someone making a slightly bigger quantum computer, and all of that work you just did is for nothing. So we're now looking at different ways of doing cryptography. And this is a thing that NIST are working on. So the National Institute for Standards and Technology have recently published proposals that are cryptographic systems that don't use number factoring, but that we think are really, really secure. So the aim is to try and come up with new ways of doing cryptography that don't worry, or at least don't worry so much about quantum computers.
Gotcha. Wow. Thank you so much for that. Mark, I want to thank you for your time and for your great work that you are doing in Quantum Village Victoria, which is also going to join us hopefully in part 2 of the Quantum Village, which also is an instrumental part of the Quantum Village, will give us a different perspective about this amazing effort that you guys are doing for the community. I want to thank you for your time and for the work that you're doing.
A pleasure. Thank you so much for having me.
I want to thank everybody also for watching us as well. I'm going to invite you to go to EPCC TV YouTube channel. There's a repository of different episodes that are related to each other, of course, because this is the Hackers Corner. And I also want to invite you to go to the hackthevoter.org, which is the website that you can see right here. And we can invite you to go and participate to the different workshops, professional development, and of course the competitions that we have. My name is Christian Servín. I want to thank everybody, and I'll see you next time. Meanwhile, happy coding, everyone.